These two methods, as we saw, were based on experiences and therefore are called as empirical methods. Okay, because there is no concrete mathematical base or derivations for this one, and all the formulae that we tabulated for both the methods were based on the trial and error or experience tests done by Ziegler-Nichols or Cohen-Kuhn or other scientists. Okay, so these two methods were empirical methods, whereas the frequency response method has a concrete mathematical base of frequency response methods in the uh, standard control theory, linear control theory that we based on Bode plots. Okay, and especially stability determined by their margins, whether the system is stable or not, is determined by the margins, gain margin and phase margin. These were the two criteria. Those are to be satisfied so that the system to be stable. So, what do these P, I, and D controllers has to do with the stability then? Okay, so for a given system, if we know the Bode plot, we can find the gain and phase margin, and both margins, if they are positive, then the system is stable. If both gain margin and phase margin is zero, that is omega GC is equal to omega PC, gain crossover frequency and phase crossover frequency is same, the system will be marginally stable. And if the omega GC is greater than omega PC, that is the gain crossover frequency is larger than the phase crossover frequency, the system is unstable, right? So now the tuning of the PID controller involves adjusting the KP, KV, and rather KP, KI, and KD, or TI and TD in such a way that the gain margin and phase margin are uh, positive, and therefore the system will be stable. And we have seen that the standard value generally taken in the industries are the gain margin of gain of 0.56 and phase margin of 40 degrees. So if the gain is less than 1, the system is stable, but for in practical purposes, the gain is criteria taken is 0.56 gain margin, and the phase margin, though the phase margin of 1 degree also satisfies stability criteria, but practically to have some tolerances, 40 degrees phase margin is required to have a stable system. So our stability criteria of gain and phase margin will be 0.56 for gain and 40 degrees for phase. This we have already discussed. Okay, let's go to the uh, presentation now, and let me share. Let me share the screen. So we are discussing the frequency response method. By the way, all these three methods are very important from exam point of view, because uh, not only one for 10 marks, you may be asked to explain one, two, or three methods. Okay, so the question in a day or two, I'll be giving you question bank also, first three chapters, and assignment also, assignment number one on typically chapter 1, 2, and 3. So by tomorrow or day after tomorrow, I'll be giving first assignment and later the second assignment. So what I was talking about was these methods, tuning methods, and there are frequent questions on PID tuning methods. You may be asked to explain uh, one method, two methods, or all the three methods in a single question consisting of 10 marks. Okay, so these methods are of utmost importance, not only from knowledge point of view, also from exam point of view. Okay, the numerical problems may also be asked, that simple problem that we have already discussed. Okay, so these are this already we have discussed. Okay, stability criteria, right? So this should be 40 degrees, right? And 5 dB corresponding 5 dB gain margin corresponding to about 0 absolute gain of 0.56, margin of 0.56. Okay, so this we have already done to solve the problems. And now let's do tuning, using how to tune PID controller using frequency response method. Okay, the tuning operations, as we know, involve the adjustment of controller parameters, that is KP, KI, and TD, until the stability is achieved by appropriate gain and phase margin. So our criteria will be the gain margin and phase margin. Okay? If the transfer function of all components are known, the body plot is drawn and the gain and phase margin are determined analytically. What does this mean? Which component we have in the process control loop? We have sensors, we have comparing elements, we have controller, we have final control element, we have process, we have measuring element, that is feedback element, and all these form uh, transfer. Each and every component has its own transfer function. A sensor has its own transfer function, then controller has its own transfer function. Say it is for amplifier. So amplifier has a gain. So it will have its own transfer function. Then if there is an integral controller, then it will be 1 by S, and so derivative controller S, and so on. So every component will have its own transfer function, and if all these transfer functions are cascaded, that is multiplied, then we get overall transfer function of the system. And once the overall transfer function of the system is known, we can draw the Bode plot of the system, and then gain and phase margin can be determined by the method that we have already discussed. Okay. Uh, Another difficulty is that suppose the system is there and individual transfer functions are not known. So the system transfer function cannot be calculated. So in control systems at secondary level, we have solved such problems also, wherein the input and output is measured, okay, experimentally measured, and then uh, actually providing the input. We have measured the output, and then from that input and output, we can draw the Bode plot. And once Bode plot is known, so both the way, if the transfer functions are critically known, we can draw the Bode plot, or if the transfer functions are not known, we can draw the Bode plot experimentally by actually putting the system into work, applying the input, measuring the output. So gain and phase margin can be measured then, both the cases. So if this gain margin is 5 dB or 0.56 absolute, and the phase margin is of 40 degrees, then the system will be practically stable. Okay, actual stability requires 1 degree also, greater than 0 degree phase margin and less than 1 degree gain margin. But practically, industries have set up these standards that the gain margin should be 0.56 or 5 dB, and phase margin should be 40 degrees. Okay, so Bode plot can be drawn and gain and phase margin can be done. Okay. Now the gain crossover frequency and phase crossover frequencies are very important. Okay. So what is the significance or importance of gain crossover frequency? The system can correct any disturbances of the frequency less than gain crossover frequency. If the frequency is greater than gain crossover, the system cannot correct the disturbances. So corrective action cannot be performed by the system if frequency is greater than omega GC. Okay, so the tuning operation is based on the fact that gain of each mode, that is P, I, and D, have particular effect on the system body plot. As KP is changed, KI is changed, and KD or TD is changed, the body plot will also change accordingly. Okay, so by adjusting these gains, body plot can be altered, can be changed until the gain and phase margin requirements of the stable system are achieved, meaning 0.56 and 40 degrees. Okay, so this is what is meant by tuning using frequency response method. So adjusting the KP, KI, KD or KP, TI and TD for required values of gain and phase margin so that the stability is achieved. This process is called as tuning using frequency response method. Okay, so let's take one by one. Okay. Frequency response method, tuning proportional action. So only P controller is there. We will see for the individual actions how to what are the expressions and how to adjust it. You individually proportional action, then derivative action and control integral action, and then we can adjust this for PI, PD, and PID. Okay, so let's consider the proportional action now. Proportional mode control simply multiplies the gain curve by a constant and independent of frequency has no effect on phase because it's a gain that is multiplying factor only, right? Gain is a unitless number, right? So it's a constant. Thus, if the gain curve is found for a particular gain, say for a file, then gain curve at any other gain, that is 10, can be found by multiplication factor of required value. So if the gain curve for gain of 5 is known, then gain curve for gain of 10 can be obtained by multiplying the whole gain curve using multiplying by 2, right? So at if the gain curve or gain plot at any proportional gain Kp is known, then can be found at any other proportional gain Kp2 suppose just by multiplying by the factor. Okay, thus whole gain curve can be moved up for increased gain and moved down for decreased gain. Okay, it can be shifted whole gain curve, that is Bode plot. Gain plot can be shifted up or shifted down. If the gain is increased, whole the plot will be moved up and whole plot will be moved down if the gain is decreased. Okay, if you remember the uh, gain plot for a say ki upon 1 plus ts, okay, k upon 1 plus ts. So for k it's a constant, right? 20 log of k, and for 1 upon 1 plus ts it is up to cutoff frequency, up to corner frequency it is 0, and then minus 20 dB slope. All these this you have already done in control systems. So if this k and 1 upon 1 plus ts is are the only two factors, then resultant factor will be 1 upon 1 plus ts curve, okay, or that Bode plot plus added this 20 log of k will be shifted up. Okay, if the gain is less, then it will be shifted down. So that is the meaning of the whole gain curve can be moved up or down, moved up for increased gain and moved down for decreased gain. Okay, the increased gain increases, that is extend the range of frequency controlled by the system. That's it. Okay, gain, the amplifier gain is increased, then the range, okay, take the proportional band will decrease. Okay, increase rather. Okay. Expression for gain contributed by integral controller. Integral meaning of no. This is, please read this as not proportional. It is integral. Okay. Please read this as integral controller. Okay. Uh, excuse me, please, for a moment. Okay. Just a minute. Please bear with me. Okay. So please read this as tuning of not proportional. This is proportional, and this one is integral control. Okay. So expression for gain contributed by integral controller is integral gain will be ki upon omega. Okay. How uh, what is integrator? What is the transfer function of integrator? 1 by s, right? 1 by s is the transfer function of integrator. So if the gain is ki, integral time gain is ki, then it will be 1 ki upon s, right? So going to the j omega, replacing s by j omega, it will be ki upon j omega, and magnitude of the gain, rather magnitude of this transfer function, mod of this transfer function will be ki upon root of 0 square plus j omega square, right? So this will come out to be ki upon omega only, and we have seen that 1 by s has a phase plot of maximum phase plot of minus 90 degrees. Okay, a factor of 1 by s in a Bode plot has a phase of ranging from 0 to 90 degrees as omega increases, and gain is ki upon omega. Therefore, gain is inversely proportional to the frequency ki upon omega. Integral gain, total integral gain is inversely proportional to the frequency omega. This means that more gain at lower frequencies and less gain at higher frequencies. Okay? Therefore, there is some frequency called as breakpoint at which the gain stops increasing and the curve becomes flat. Okay? So, at very low frequencies, the effect of integral factor reduces and the curve becomes flat. Okay? I'll show you this in the figure in the next slide. Okay, so remember that as the gain increases, with the frequency. Sorry, the phase shift goes more and more towards 90 as the omega increases, the frequency increases, lagging as the frequency increases, and to 0 as the frequency decreases. Okay, so this is shown in the next figure. Let's read this as derivative control then. Okay, this was proportional. The title I forgot to change this one. This is integral. This is proportional. This is integral. Okay, and this is derivative. Okay, so derivative gain, we know it is kd into, this is a factor of s. It has a positive slope of 20 dB per decade in the Bode plot. Okay, and phase is from 0 to 90 degrees as omega increases from 0 to infinity. Okay, so derivative gain is kd into omega, and phase, sorry, this is derivative phase. There are much mistakes in printing now here while typing. Okay, sorry for that. Read this as derivative phase. So derivative phase is plus 90 degrees. In integral, it's minus 90, and gain to be ki upon omega. This is one factor of 1 by s, and this is factor of s. This is in numerator. S is in numerator, and this is s is in denominator. Right? So gain is kd into omega, and phase is plus 90 as omega increases. So the gain is directly proportional to omega. As the frequency increases, gain also increases. As the frequency decreases, the gain also decreases. Okay, and phase increases with increase in frequency. So as the gain increases with increase in frequency with certain upper limit, limiting frequency at which the gain becomes constant and phase shift becomes zero, right? So therefore the derivative control can be used to increase the gain at higher frequencies and move the phase away from minus 180. Since it is plus, so we can increase the integral phase, okay, as the frequency, higher frequencies minus 180 and plus, so phase margin will increase, okay, and system uh, at 180 the instability begins, but if some integral derivative phase is added to it, minus 180 say plus 45, so 45 degrees phase margin will be increased using the derivative uh, control action, right? So all the three are shown in one. Look at this. This is open loop gain. This is frequency, okay, log of frequency, of course, and this is phase in degrees, and this angular frequency, that is log of angular frequency, log of omega, right? So look at this figure. Okay, so Kp is equal to 6. So 20 log of 6 is this line. Can you see? 20 log of 6 is this line. Okay, whereas this is 1 by s integrator. Okay. Integral control action minus 20 dB per decade. So Ki is taken as 1. So it is 1 by s. So minus 20 dB per decade. Okay, and this is the break frequency as the gain is inversely proportional to frequency. It is Ki upon omega. Ki is 1, considered as 1, therefore it is 1 upon omega. So as the frequency decreases, okay, the gain increases, and at a particular break frequency, is approximately 0.04 or something like that, right? At that frequency, this effect of increase in gain with frequency ceases, stops, and the curve becomes flat. Okay. Similarly, uh, in case of derivative control action, the gain increases with frequency. Gain increases with the frequency up to certain value of frequency, and then it becomes flat. Curve flat, stops. Okay. So derivative and integral control actions are opposite to each other, whereas the integral control action is independent of this phase or something like that. Okay. So gain doesn't depend upon the frequency. Okay. Whereas as far as the phase plot is concerned, see the phase plot for proportional control. So proportional control gain has no effect on frequency, has no effect on proportional gain, right? So as the frequency increases or decreases, proportional gain remains constant at this one. Whereas, right? Whereas for integral control, as the frequency increases, the phase increases towards negative 90, minus 90, from 0 to minus 90, and then it becomes minus 90 at a particular remaining frequency. Whereas for derivative control, it's plus 90 at 0 frequency, and then it decreases to 0 as frequency becomes infinite. So this is the phase plot for all the three control actions. Okay. So what we are interested in is the gain margin and phase margin. For that, we will see some examples after this one. So in this way, the tuning of individual controllers. This is proportional controller. Integral controller has this action, okay, and derivative control has this action. Okay. So this is the resultant of all the three. Okay, let's have some example on this one. Might be I'll terminate the lecture in between because the chapter ends. We will start new chapter PLC, Programmable Logic Controllers, tomorrow. Tomorrow's lecture. Rather, uh, we have missed yesterday's lecture, na? So we'll plan the lecture tomorrow or day after tomorrow, and in that we will start our new chapter. So today, with the end of this topic, frequency response method for tuning, we will end this lecture. So let's have some example. Excuse me please for small disturbance. Just bear with me. Just for 2 minutes, please hold. Sorry for this disturbance, and let's solve this problem. Okay, find the decrease in proportional gain that will make the system with following Bode plot stable, right? So Bode plot is given, and from this Bode plot, we have to identify, rather, make the system stable. Okay, so look at the Bode plot. The gain plot is something like this. This is frequency log of omega, and uh, say this one is 0.001. This is 0.01. This is 0.1, and this is 1, right? So, and this is the gain. It starts from 6 and then goes up and then goes down and down and down up to 0.5. Whereas the phase starts from about 130 and it decreases here up to say minus 220 or so on. Okay. So what we will determine from this one again, the gain crossover frequency and phase crossover frequency, and we will find the margins, gain margin and phase margin from that. Okay, and we'll decide whether the system is stable or not with respect to our standard criteria of gain margin of 0.56 and phase margin of 40 degrees. Okay, so let's see. Let's measure the gain margin then. Where is the phase crossover frequency? Phase crossover frequency is there where the phase plot crosses minus 180. So this is omega PC, right? So omega PC, when it is projected over the gain plot, so this is somewhere 0. This is zero point 0.5, this is 0.6, 0.7, 0.8, 0.9. So it is approximately 0.65 or zero point 0.7, rather 0.7. So this phase crossover frequency when projected on gain and gain measured, so this gain margin comes out to be 0.7. Okay, so 0.7 meaning actually we have a criteria of 0.56. Okay, though less it is less than 1 and the system will be stable, but our criteria is of 0.56. Okay, so system is not that much stable as per required criteria. Okay, so system failed to satisfy 5 dB gain margin, that is 0.56 at 180 degrees, because the gain is 0.7 instead of 0.56 or less. Okay, so what we have to do then, if we reduce the proportional gain, then what will happen? All the curve will be moved down, right? The curve will move down and these frequencies will come towards left, shift towards left, right? So instead of 0.7, then it would reduce to 0.56. So that much gain has to be reduced, proportional gain has to be reduced. And remember that the proportional gain hasn't any effect on phase plot. Okay. By the way, the next thing is find the phase margin. Where is the gain crossover frequency? The gain crosses 1, okay, unity gain at this frequency, right? At this frequency. So this corresponds to 0 dB. Okay, absolute 1 corresponds to 0 dB. So this gain crossover frequency comes at this one, okay, and this seems to be 160 or something like that. Okay, what point it corresponds? It cuts here. So if it is projected on this, okay, what is the value? Okay, 120, right? It's 120 then. So this is 120, right? So 120 meaning 180 minus 120 is 60 degrees. So phase margin of 60 degrees, meaning 40 degrees criteria is satisfied. So as far as phase margin is concerned, the criterion is satisfied, but the gain margin criterion is not satisfied. So what is the solution then? The solution should be such that the proportional gain has to be reduced, which will affect only the gain and not the phase. Okay, the solution is to reduce the proportional gain. So reducing proportional gain, I can move the curve down, and then this gain crossover frequency will move leftwards. Okay, this point will shift on this side, and then the gain gain margin will be 0.56 or something like that, and then the system will be stable. Okay, so this has to be done then. Okay, so this change in proportional gain will not affect the phase. Okay, so by what factor it should be reduced then? Okay, by what factor? Actual gain, original gain is 0.7 and we want 0.56. So gain should be reduced by a factor of 0.7 divided by 0.56. So by this much factor, if the gain is reduced, then the system will be stable with a gain of 0.56, right? Criterion. So proportional gain has to be reduced by a factor of 0.7 divided by 0.56, right? Next, the second example. Are you understanding this or not? Right? Anyone? You can type in chat box. Understanding or not? Can you hear me? Am I audible? Okay, understanding the effect of change in gains on body plot? Understanding or not? Okay, let me continue then. So this was example 1 then. Okay. Now, the similar example where the gain is given, proportional gain is given. Exactly similar example is there. Consider the body plot given, okay, for some process and controller with proportional gain of 10. Kp is given as 10. Show that the system is unstable and find the proportional gain for satisfying gain and phase margin. Okay. So first we have to prove that the system is unstable, and then we have to find the proportional gain for satisfying gain and phase margin. Okay. See, this is the original gain plot, and this is the phase plot. Okay, this is the given. With this, what are the gain and phase margins? This is unity gain So projecting it down, the phase margin seems to be very small, right? The phase margin seems to be very small. Whereas, sorry, this is minus 180, no? Okay, this has to be projected. This, where is that? Minus 180 degrees. This has to be projected up, and this will be the gain margin then. Okay. Similarly, unity gain crossing is here, this point, 5 radians per second, and the phase margin. So both gain and phase margin are very small. See, this is 180 and this one is about 160 or something like only 10 or 170 or something like that. 10 degrees of phase margin it seems to be, and gain margin is also higher than 0.56. Okay, this point projected on this axis. So this is zero point 0.5. If this is 0.7, 0.8, something like that. Let's see how much it is. From Bode plot, it can be seen that the gain crossover frequency is 170 degrees, right? This gain crossover frequency, unity gain, is 170, right? And for this phase margin of 10, because 180 minus 170 is 10. This means that the criteria of 40 degrees phase margin is not satisfied, right? Secondly, the gain at phase crossover frequency is approximately 0.8. Look at this. Okay, this is phase crossover, and if I take it this point, it is zero point 0.8 or something like that, right? So zero point 0.8 is much higher than 0.56 because our criteria for a stable system practically is 0.56. So that also. Secondly, the gain at phase crossover frequency is approximately 0.8. There is gain margin of zero point 0.8. This means that the gain margin is less than 1. Okay, but criteria 0.56 gain margin is not satisfied, and thus the system is unstable. So we have proved that the system is unstable using actually measuring the gain and phase margin on the given Bode plot. So what has to be done then? Similarly, in case of last example, what we did, we will change the gain in such a way, proportional gain in such a way that the whole curve is moved either up or down. In which direction it has to be moved then? Both margins are less. Okay, so to increase both margins simultaneously, the curve has to be moved down. Okay, if the whole curve is to be moved down, what has to be done then? Proportional gain has to be reduced. For increase in proportional gain, the curve will move up. For decrease in proportional gain, the Bode plot curve will move down. So decreasing initial gain is of 10. Okay, gain given in the problem is 10. So that has to be reduced. Okay, and let's see how much it is to be reduced then. Now to make the system, both gain and phase margin criteria should be satisfied. It can be seen from Bode plot that if the entire gain plot is moved down by a constant amount as shown in figure with no effect on phase plot, then stability criteria can be satisfied. This is done by changing the proportional gain because it affects the gain only and not the phase. Thus, if the gain is reduced by a factor of 1 by 2 to achieve both margins, and the new proportional gain should be 10 by 2, that is 5. This is seen from the graph. See, this curve is for a Kp is equal to 10, whereas by reducing it to half, Kp is equal to 5, whole the curve will be moved down, and measure the gain margin and phase margin for the new Bode curve. Okay, what is the phase crossover frequency? The phase crossover frequency is 5, but now it is intersecting the gain curve at 0.5. So new gain margin is 0.5, which is less than 0.56, right? And the gain margin criteria is satisfied now for the stable system. Similarly, the unity gain frequency, that is omega GC. Omega GC is here now for a new curve, and projecting it down, so it intersects. This will intersect approximately at this point, okay, where it's minus 140, right? So 180 minus 140 gives 40 degrees phase margin, and then both gain margin criteria and phase margin criterion is satisfied, and the system will be stable then. In this way, by reducing the proportional gain, whole the curve is moved down, gain curve is moved down, and the phase curve is not at all bothered. It is not changed because phase is independent of the proportional gain. Okay, so it is independent of omega. So only gain curve will be moved down, and that has served our purpose of reducing, rather increasing the gain margin and the phase margin. In this way, uh, we can change. Actually, in practice, all the KI, KD, and this KP are also changed accordingly so that we can get perfect shape. Okay, here only we have taken the examples of proportional gain, change in proportional gain only for simplicity. In actual practice, the KI and KD, that is TI and TD, has also to be changed to get a perfect shape of the Bode plot. Okay, which, it is changed in accordance with our required gain margin and required phase margin, right? In this way, tuning of PID controllers, adjusting the gains of PID controllers is done using frequency response method. So you must have understood the application of Bode plots for process control system. Okay, so this is too much practical. Understood? So about 90%, rather 85 to 90% of the all practical systems in the industry use the PID controllers, and they use, of course, now the advanced methods are used for adjusting this. Digital controllers are used, but still the basic methods remain the same. Okay? These uh, Ziegler-Nichols or Cohen-Kuhn or this frequency response methods are still used. Okay, but now the modern tools like MATLAB and all are used to adjust this one. Okay, so this is what is about the tuning of the PID controllers. Okay, so here we end our third chapter. Okay, and then we will be not be starting the chapter today. Start our chapter tomorrow. There is a question by Rishikesh, point 0.8 by point, why not 0.8 by 0.6? So if it satisfies our gain margin and phase margin criteria, see, by 0.8 by 0.6, if the gain margin criteria is satisfied, phase margin criteria is satisfied, might be a gain margin criteria will be satisfied by that, but phase margin will not be satisfied if you draw actually, right? So at reducing it by half, I'm getting the phase margin of exactly 40 degrees. Look at the graph, okay? And that's why it should be something more than that, okay? So if it is reduced by 0.5, 0.8 by 0.56, then phase margin criteria is not satisfied, okay? I won't be getting 40 degrees phase margin. So it's something more than that, okay? So this is what we have to go in this chapter. Especially these three methods are very important. Their procedures and even the numerical problems I haven't seen. So this subject has changed. Actually, this was in sixth semester, and some syllabus also was it changed. Uh, First three chapters were there in at the sixth semester uh, in previous syllabus. In new syllabus, only one exam has been conducted and only one paper is there. I think I have shared that paper with you. But when I saw the previous papers of 2012 revision of the syllabus, okay, so there were questions on this part, third chapter, and especially tuning part. Repeatedly, there were questions on this one, tuning of this and all methods. Okay, so you must know and will be should be able to write uh, all the methods and explain all the methods, all the three methods rather. Okay, open loop transient response method, then Ziegler-Nicholas methods, and this frequency response method. Go briefly, but you have to explain all the methods or as asked in the exam, whatever the question, one, two, or three, all the methods. Okay, so that's it from today's lecture. Then we will start our new chapter, programmable logic controllers. Probably in tomorrow's lecture, I'll give you time. Okay, so let me mark the attendance then. By tomorrow or day after tomorrow, I'll be putting the question bank also and the first assignment also. Okay, and during this Diwali vacations, I'll be putting the second assignment also. Okay, though we have not completed the syllabus, but you must have you will be prepared for this second assignment also. I'm planning one assignment on PID tuning using MATLAB also. Let me see how can I do it. Have you done PID tuning experiment in practicals using MATLAB? Yes or no? Any experiment on PID tuning using MATLAB, ISDL lab? So if it is there, if it is not there, I'll be giving one assignment based on that also. Tuning a PID controller using MATLAB. Okay, let me see there. Okay. Till then, thank you very much. Okay, so see you tomorrow then. Tomorrow, day after tomorrow, wherever it is possible. I will let you know the timing of yesterday's missed lecture. Okay, I'll reschedule it and let you know the time. Okay, thank you then.